Here is an introduction to chemical kinetics. We explored different reactions in a number of ways. As we know, we have learned about the stoichiometric relations of a particular reactions. We know how to balance a chemical equation. We have also learned to what extent a particular reaction would take place by study of its chemical equilibria. We find that most of the reactions are reversible reactions and they attain an equilibrium state, and thereby we determine the extent to which the product could be obtained or the reaction would proceed. Not only this, we have studied the thermodynamics of the reactions and we have determined the feasibility of a reaction, whether a reaction would occur or not, depend, uh, depending upon the certain terms involved in studies of thermodynamics, such as delta G, delta H, and delta S, enthalpy, entropy, and Gibbs free energy. That gives us an idea about the feasibility of the reaction. But not only this, we have to explore the reactions again with respect to its rate of the reactions. We find that many reactions are very fast reactions. Certain reactions are instantaneous reaction. They are very quick, and there are reactions which are very slow. So accordingly, we have to uh, control the rate of the reaction or the speed of the reaction. Of course, there are methods by which we can control the speed of the reaction or the rate of the reaction using suitable catalysts or the conditions of the reactions. Not only this, we have to study the mechanism of the reactions. What are the steps of the reactions which take place? What are the factors which govern the speed of the reactions? So, all this is studied in what is known as our studies in chemical kinetics. Kinetics is a word which has been derived from kinesis, a Greek word, of course, and kinesics means movement. We need to find out at what rate the fuel burns in internal combustion engine. What will be the time period required for decay of a vegetable or food products? So that way we need and we have to control the rate of decay or rate of a particular reaction. So, what is meant by chemical kinetics? How to define chemical kinetics? Kinetics is the branch of chemistry which deals with the rate of the chemical reactions, as I have already explained to you, factors affecting the rate of the reaction, and also the mechanism of the rate of the reaction. So, 3 points here to be noted carefully. Rate of the chemical reaction is not the only study in chemical kinetics. Thereafter, we explore the conditions and the factors which affect the rate of the reaction and what are the steps of the chemical reaction, which is known as mechanism of chemical reaction, are all explored or studied in chemical kinetics. Now, how the rate can be determined or rate can be expressed when we call rate means it has a concern with time period. So just as we calculate the rate of movement of a particular body, similarly we find out here the change in concentration of the reactant or the change in concentration of the product with respect to time, and that is known as the rate of the reaction. Rate of reaction is the change in concentration of any one of the reactants or the products. Find it any one. You can. It depends upon our convenience, which can be easily determined. Any one concentration is the important term, and concentration we know is reported in terms of moles per liter, and since it is a factor of time, the unit for reporting the rate of the reaction is moles per liter per second or mole liter inverse second inverse. But if it is a gaseous reaction, we report in atmospheres per second. So that's there. And this is very well represented in your book through this figure where the a plot of concentration, change in concentration of the reactants with respect to time is given, and you find a curve like this. known as T2 minus T1. So here is a very good figure which is given in your book and which explains the rate of change of concentration of the reactants or even the concentration of products with respect to time. At a particular period of time, instant of time, say T1, the concentration of the reactant is R2, and after a lapse of time, which is given by T2, the reactant concentration is R1. So change in concentration is R2 minus R1. Mind it, the reactant goes on used up. The concentration of the reactants gets reduced. Therefore, R2 will be higher than R1. And since there is a consumption of the reactants are being used. Therefore, this rate is reported as minus R2 minus R1. Concentration is then been written in square brackets as we know, and T2 minus T1 represents the time period. So this can well be represented as minus delta concentration of the reactants. Delta means change in concentration of the reactants divided by the time period. And RAV means average rate of reaction. So this way we can find out the average rate of reaction with respect to the reactant. Any one of the reactants, depending upon our convenience, can be used if there are more than one reactants. Mind it, the concentration of the reactant goes on increasing, whereas the concentration of the reactant goes on decreasing. Mind the concentration, the average reaction rate is positive, whereas in case of reactant, we have to use a negative sign. Why? Because the products goes on increasing, and therefore average reaction rate is given by delta P upon delta T, the same way as we have done here in case of reactant. Now, one thing is very important that this represents a period under which the concentration has changed, and that period here is T2 minus T1. But then suppose we want to change, the concentration goes on changing with respect to time. At a particular instant of time, suppose the concentration has to be measured, then we have to plot a tangent. We have to draw a tangent over this curve, and the slope represents the rate of reaction at that particular moment or instant of time, and therefore we call it as instantaneous rate of reaction, represented as RINST. Again, please note it is negative in case of reactants, so minus dr by dt. We don't use delta here because it's a very infinitesimally small change in concentration. So just like a differential it calculates, we use minus dr upon dt, and the slope represents the change in concentration at a particular instant of time, and that is known as instantaneous rate of reaction on delta T. Again, the same point has to be noted that for products it is positive. And all these is because it is the same reaction that you consider a reactant or the product. The rate of reaction at a particular time would be the same, or a particular period it will always be the same. And therefore, this is the expression which gives the average rate of reaction. Average rate of reaction. And mandate that here, if there is a coefficient in the stoichiometric relation, that coefficient comes over in the denominator always. So writing a particular expression for average rate of reaction has become very simple. Similarly, for instantaneous rate of reaction, at a particular moment of time, we suppose there is a reaction R changing to P. R means the reactant, P means the product. So instantaneous rate of reaction will be equal to minus dr upon dt, which will always be negative, and here positive dp upon dt. D means very small period of time, and very small period change in concentration. Concentration terms are the reactant terms, we know are always represented in square brackets. Okay, then again, let us have an example here to express the rate of the reactions. Here is a simple expression for relative reaction rates. There is a very simple reaction during the manufacture of nitric acid by Ostwald process from ammonia. By combustion of ammonia at a high temperature in presence of a catalyst, this reaction takes place and you get nitric oxide and water. Of course, these are all gaseous reactions. So if you have to write down the relative reaction rates, same way we used coefficients on the denominator, reactants always negative if you are using a reactant what to represent the rate of the reaction, and this way all the reactants are the products, whatever may be the way of representation, reactants are always negative, whereas products are always positive. The rate of the products are the rate of reaction with respect to products are always positive. Let us take another example where certain data is given, and then there is a ionic reaction. Same way we can write down the rate of the reaction here. And the what is more important is that if you represent the rate of a reaction with respect to change in concentration of the reactant, then it is negative. If you represent in concentration to the change in concentration of the product, it is positive. And the coefficients, if any, in the stoichiometric relations are there, then that comes in the denominator. With all these considerations, it becomes very easy for us to write down the relative reaction rates or average reaction rates.